Let's talk about energy in physics here. To start with this topic, I will draw an object first, and this object is in the midair and it will drop. When this object is in the midair, it has potential energy stored in it. As it drops, its potential energy is converted to kinetic energy. For a simpler situation, let's say you're holding a ball in the midair and then you let go and it drops to the floor. So then we can ignore air resistance for now. Now, what caused this object to drop? It's the force of gravity. Okay, let's look at the net force acting on this object here. We know that the only force acting on this object here is the force of gravity. So that's equal to force of gravity. And we know that this is only in the y direction. Now, we know that the formula for the net force is mass times acceleration. And we also know that the acceleration is in the y direction here. And that's equal to, what's the formula for force of gravity? Negative mg. Okay, we can also rewrite acceleration as change in velocity over change in time. So we can write this as m times dv over dt. That's equal to negative mg. We can further break this down into mass times dv over dy, and dy is the change in displacement, times dy over dt according to the chain rule. And we know that dy cancel out, we have dv over dt left, and that's equal to this side, negative mg. Notice that what's change in displacement over change in time? Here, it's velocity, so we can write this as m times v times dv over dy is equal to this side, negative mg. Now, we should multiply both sides by dy. We have mv times dv equals to negative mg times dy. Okay, so since we have dv on this side and dy on this side, we should integrate both sides. So integrate mv dv is equal to integral of negative mg dy. What is the lower limit and the upper limit of the integral? On this side, we're integrating dv, so the lower limit should be v initial, and the upper limit should be v final. On this side, we're integrating dy, so the lower limit should be initial position, and the upper limit should be final position. Okay, now we can do the integral. So add 1 to the power divided by the new power, we have half mv squared. We evaluate from initial velocity to final velocity. And that's equal to this side, we have to add y, so we have negative mgy evaluate from initial position to final position. Okay, let's put the limit into the integral. We have half mv final square minus half mv initial square equals to negative mgy final minus negative mgy initial. And we know that minus is plus, so we can rewrite this as half mv final square minus half mv initial square equals to mgy initial minus mgy final. Now, let's rearrange this equation here. So we will add mgy final to both sides and add half mv initial square to both sides. So we have half mvy final plus mgy final equals to half mv initial square plus mgy initial. Okay, so that's the equation. And notice that the kinetic energy formula, we will use letter K, capital letter K, and that's equal to half mv squared. The potential energy we will use capital letter U, and that's equal to mgy. Y is the displacement. So in that case, right, we can rewrite this as, this will be final kinetic energy plus final potential energy equals to initial kinetic energy plus initial potential energy. Okay, now let's look at another example. So let's say there's a rock here that's hanging here by a rope, and then you let it swing, right? And then it will go to, let's say, this position here. So while this is in this position here, it has potential energy in it. As it let go, it swings, its potential energy is converted to kinetic energy. Okay. The sum of the kinetic energy and the potential energy is the mechanical energy. Now, let's talk about the law of conservation of energy. And we only talk about kinetic energy and potential energy for now. So it's the mechanical energy equals to kinetic energy plus potential energy. Now, at the beginning, the object may have a lot of potential energy, but as it drops or it swings or moves, right, its potential energy drops, and then its kinetic energy will increase. And when its kinetic energy decreases, its potential energy should increase. So the net change in the mechanical energy should be 0. So that means as long as the value of the total mechanical energy does not change, the mechanical energy is conserved. In other words, there cannot be external force acting on the object. And the external force could be friction, right? You cannot just convert mechanical energy into heat, which is called thermal energy. In that case, the mechanical energy will not be conserved. Okay, now let's look at it like that. This equation here, or this formula. So we have final kinetic energy plus final potential energy equals to initial kinetic energy plus initial potential energy. Now, let's rearrange this. So we will subtract initial kinetic energy from both sides and subtract final potential energy from both sides. So we have final kinetic energy minus initial kinetic energy equals to negative potential energy final plus potential energy initial. So we can rewrite this as here. Final kinetic energy minus initial kinetic energy equals to negative final potential energy minus initial potential energy, right? Because here, minus will become plus here. Now, this is just the change of kinetic energy. And this is the change of potential energy, but it's negative. So negative change in potential energy. So basically, we can say that the change in kinetic energy is the negative change in potential energy. Yeah, because that should be negative. Because when potential energy decrease, kinetic energy increase. When kinetic energy decrease, potential energy increase, right? So it's the opposite relationship. Okay, now this is just the system of only kinetic energy and potential energy, which is the system of an object that has only mechanical energy. What about other types of energy? There are other types of energy, such as thermal energy. So we're talking about a different system here. Let's say the system of the energy here, right? In this case, we have kinetic energy plus potential energy plus thermal energy. Let's say we have one more type of energy in this system. It's the thermal energy. And we know that this is mechanical energy, as we mentioned before. So this is the mechanical energy plus here, thermal energy. Okay. In this situation, let's talk about this. If energy is transformed within the system, then the change of the energy in the system is 0. Then we can say that the energy in the system is conserved. Now, if energy is transferred to or from a system by doing work on the system, then the energy of the system will change. In that case, right, the change in the energy of the system is equal to the work done. Then the energy is not conserved. The energy of the system is not conserved. Okay, now let's look at this in more detail. Now, first of all, I just mentioned work done here, okay? Now, let's look at the relationship between work and energy now. But first of all, let's look at the relationship between work done in physics and kinetic energy. Okay. When a force is acting on an object, it does work on the object. So we're talking about the force acting on the object here. So let's talk about the formula, right? F equals to ma that we know from Newton's second law of motion. Okay, what do we do next? Of course, we can rewrite acceleration as change in velocity over change in time. So that is mass times dv over dt. And we're doing the similar things as what we did before. We can break this further down according to the chain rule into dv over, now this time I will use the letter s, ds times ds over dt, right? S stands for displacement here, because we're not talking about the displacement in the y direction. This is more like for the horizontal direction here. We may normally use the letter d for displacement, but since the derivatives start with the d, we don't want to write double d here. So we just write ds this time. We use s as displacement this time in this derivation. As you can see, ds and ds cancel out, all you have left just dv over dt, right? So it's the same as this here, nothing changed. But you know that change in displacement over change in time is velocity. So we can write this as force equals to mass times velocity times dv over ds. Now, we should multiply both sides by ds. We have force times ds equals to mass times velocity times dv. Now again, we have ds on this side, we have dv on this side, we should integrate both sides. Okay, so let's do the integral. Equals to integral mv dv. Okay, now, what's the lower limit and the upper limit of the integral? On this side, we're integrating ds. So it should be from initial position to final position. On this side, we're integrating dv. So it should be from initial velocity to final velocity. Okay, now we can evaluate the integral. We can do the integral. So for this one, is f times s evaluate from initial position to final position. Equals to this side will be add 1 to the power divided by the new power. We have half mv squared evaluate from initial velocity to final velocity. Okay, now let's put the limit into the integral. We have f times final position minus initial position equals to this one will be half mv final square minus half mv initial square. Now, what is this equal to? In the bracket, it's change in displacement, right? So we can write that as f times change in displacement equals to, what's this? Change in kinetic energy, right? So delta K. Now notice that, what's this equal to? This is equal to work done in physics. So we can write that as W equals to change in kinetic energy. So what does that mean? That means the work done to the object can change the kinetic energy in the object. Okay, let me write this. Work done to the object changes the kinetic energy of the object. Okay, now over here we can say that the formula for work done is force times change in displacement. Now normally maybe you write this as delta D, right? So you have work done equals to force times delta D, right? Maybe you write like this normally. Now, according to this formula here, right? The force only does work to the object if the object is displaced. So delta D cannot be 0. The object has to move from one position to a different position in order for this to be considered work done, right, on the object. Next, think about this in a different example. Let's say this is the floor, and there's an object here. And then this object is being pulled by a force. Okay, now you want to calculate the work done to move this object, right? What would be the formula for this? It's not just force times displacement, because the force is inclined at an angle. So let's look at it here. So here, you have to break this force into component of vector, like this, right? So that's an angle here, theta, let's say. But what do we care about? We care about the horizontal component here. Now, what's the horizontal component here? According to the trigonometry, we know that this is force times cosine theta, right? So the work done to move this object will be equals to force cosine theta times change in displacement. Okay, let's use delta D, right? So that would be the formula for the work done on this object. Okay, next, we just talk about work done and kinetic energy. How about we talk about work done and potential energy now? So work and potential energy. Okay, now, first of all, let's bring back what we talk about here. Work done is equal to change in kinetic energy. So work done is equal to change in kinetic energy. I'm going to write it this way. Change in kinetic energy equals work done. However, for this work done, we have to break it down into two different types of work done. And that's equal to work done by conservative force plus work done by non-conservative force. Okay, so now, what would be an example of a conservative force? Let's say conservative force. An example would be gravitational force. Gravity force. What would be the example of non-conservative force? An example would be friction. Now, think about it this way. In the early example, when we talk about an object dropping, right? An object just dropped from the mid-air, right? And what caused this? It's the force of gravity, right? That's causing this object to drop. So it has potential energy here, and then it starts dropping. So its potential energy is converted to kinetic energy, and at the same time as it drops, its potential energy is decreasing. So to associate potential energy with work, we should associate potential energy with gravitational force, right? So which is a conservative force. So we can associate work done by conservative force to the potential energy. However, think about non-conservative force, friction. What does friction do to an object? It's going to act in an opposite direction of where the object is moving, and at the same time, it's causing heat and thermal energy between the object and the surface, right? But that is converting the mechanical energy into thermal energy. So we cannot really associate potential energy with non-conservative force. So in that case, we also know this, right? We know from earlier, right? Change in kinetic energy is equal to work done, and change in kinetic energy equals to negative change in potential energy, as I mentioned here. Here. Then we can associate work done by conservative force with change in potential energy. Notice that this is a negative sign. Because think about that, right? As the work done, which is as the work done by a conservative force, which is gravitational force, right, to the object, as it drops, its potential energy is decreasing. So it's negative sign, okay? Now, we can replace this into this equation here, right? Into the work done by conservative force in this equation. So we will have change in kinetic energy equals to negative change in potential energy plus work done by non-conservative force. Now, add negative delta U to both sides, we have change in kinetic energy plus change in potential energy equals to work done by non-conservative force. Now, what is change in kinetic energy plus change in potential energy? That is change in mechanical energy. Notice that, right? When change in mechanical energy is 0, we say that the mechanical energy is conserved. So basically, at this time, work done by non-conservative force has to be 0 in order for mechanical energy to be conserved. In other words, there cannot be an external force such as friction, right? Non-conservative force to act on the system. Okay, now, again, in this situation, this is only an isolated system of an object with mechanical energy. Now, let's talk about a system of energy, right? With more than just kinetic and potential energy. Let's ask this question here, or answer this question. What about an isolated system with thermal energy? There are more different types of energy, but let's only talk about thermal energy other than kinetic energy and potential energy here. Okay, now, what's the symbol for thermal energy? We will use this one, E subscript TH. Okay, now, how will you say the energy is conserved in this system with kinetic energy, potential energy, and thermal energy? Because before, with the system that we have is the kinetic energy and potential energy. So we say that the mechanical energy is conserved. But in this case, we have to talk about the energy in the system with all these three energy is conserved. And what will be the case? Now, we know that energy of the system here is the kinetic energy plus potential energy plus thermal energy. At the same time, we also know that in this system, we have both the mechanical energy plus the thermal energy. Now, earlier we talked about what it means by the mechanical energy to be conserved. Now we want to talk about this whole system of energy to be conserved and what it means by that to be conserved, which includes the thermal energy here, right? Okay, so now in this case, we have to break down work done by non-conservative force into two more works, which is work done by dissipative force plus work done by external force. Okay, So now, let's look at what we talked about here earlier. Now here, change in kinetic energy plus change in potential energy is equal to work done by non-conservative force, right? Then we can rewrite this equation like this. Change in kinetic energy plus change in potential energy equals to work done by non-conservative force. Now we can replace work done by non-conservative force with this. So change in kinetic energy plus change in potential energy equals to work done by dissipative force plus work done by external force. Okay, now, how do you associate change in thermal energy with this work done? Now, think about this. External force is external force, right? Outside the system. How about within the system? What can be the work done? Think about it like that. What's an example of dissipative force? An example would be friction. Now, wait a minute. I just talked about an example for non-conservative force to be friction. And now, I'm talking about an example for dissipative force to be friction. Why? Because dissipative force is also non-conservative force. Okay, now, that will make sense now, right? If friction can actually convert, right, the energy, right, like the mechanical energy into thermal energy. Because friction always acts in the opposite direction, right? We can write that the work done by, so negative work done by dissipative force is equal to change in thermal energy. So the dissipative force, friction, can cause the object and the surface to generate heat, which is thermal energy. Now, why is it negative? Because the friction just always acts in the opposite direction of where the object is moving. So it's negative. So we can also just multiply both sides by -1. We have work done by dissipative force equals to negative change in thermal energy. Okay, now we can replace this into this equation here. We have this. Change in kinetic energy plus change in potential energy equals to, now this is negative change in thermal energy, plus work done by external force. Now add change in thermal energy to both sides. We have change in kinetic energy plus change in potential energy plus change in thermal energy equals to work done by external force. What is this equal to? Now we know that the energy of the system is kinetic energy plus potential energy plus thermal energy. So this change in all this is a change in the energy of the system equal to external work done by external force. Now, does this look familiar to you? This is what I just talked about earlier. Here. Oh, here. So this part here, right? Situation 1, change in the energy in the system is 0. Situation 2, change in the system of the energy is equal to the work done, but this will be external force, right? Work done by the external force. Now notice that what I just mentioned before, right? If the energy is transformed within the system, right, the change in the energy of the system is zero, then the energy of the system is conserved. But if energy is transferred to or from a system, basically like work done by external force, right? Transferring energy to the system or transferring energy out of the system, then the energy of the system is not conserved. Then the change in the energy of the system is not equal to zero, right? So that is change in the energy of the system, which is the work done by the external force, right? Caused by the work done by external force. So same as what I'm talking about here right now, right? That means if the work done by the external force is equal to zero, we have change in the energy of the system equal to zero. Then the energy of the system is conserved. However, if the work done by external force is not equal to zero, then the change in the energy of the system is also not equal to zero. Then the energy of the system is not conserved. Okay, now just want to summarize a little bit, okay? Earlier when we talk about this, the mechanical energy is the kinetic energy plus the potential energy. So the change in mechanical energy is the change in potential energy plus the change in kinetic energy. So in order for mechanical energy to be conserved, that cannot be non-conservative force like friction that convert this energy to thermal energy, because there will be change in mechanical energy if the mechanical energy is converted to thermal energy, right? So the mechanical energy is not conserved. Now, in this situation here, we look at the system that has more than just kinetic energy and potential energy, which includes thermal energy. So it's another scenario of the system of energy to be conserved, right? That we're talking about. So in order for the system of the energy to be conserved, there should only be transformation of energy within the system, which is kinetic energy, potential energy, and thermal energy. So if you look at it like this, if the net change in discrete energy is zero, which is work done by external force is zero, right? Then the energy in this system is conserved. But if the change of these three types of energy is not zero, which is this case here, right? Then the energy of the system is not conserved. In other words, we can say that, right? We can see that as long as the value of the total energy in the system is not changed, then the energy is conserved. Hope you enjoyed this video. Don't forget to subscribe to my channel. Thank you.